Hello, Pulkesh. Are you there?
Yes, Prakash, am I audible?
Yeah. You're audible. Would you want to check your screen sharing in presentation once?
Yeah, sure.
You can share your screen, sir, to just check.
Prakash, is it visible to you?
Not yet, sir.
Dr. Digambar, can you see
No, sir, not yet.
my entire?
Yeah, it is sharing. Yeah. Mm. No, it is not.
What about now?
Yeah, sir. Now it is.
Okay.
Yeah.
You can
It is
make it
showing the
as
whole
a
screen,
slideshow
not
so that it.
presentation.
Just hold a second.
Sir, first make it as a slideshow, then share your screen. It will be
Okay.
visible then. Yes, now it is visible clearly.
Okay. Thanks for confirming.
Sir, for just check, just change the slide so that we can see whether it is same replicating or not. Yeah, sir. Yeah, good. Very nicely. Yes, sir. Now we are able to do this.
So we'll start in another 5 minutes, right?
No, so I welcome you, sir. I'm Dr. Digambar Puri. I'm co-coordinator of this workshop. It's an 1 week ATAL FDP, 1 week online ATAL FDP on Geo-AI innovations in AI for improved spatial data processing. I will give you a small introduction of today's speaker. Dr. Pulkesh Das holds a PhD degree from the Indian Institute of Technology, Kharagpur, India, and conducted the postdoctoral research in the School of Forest Resources at the University of Maine, USA, under the guidance of Dr. Perinaz. With a robust academic foundation, he earned his bachelor's degree in physics and the master's degree in remote sensing and GIS from Vidyasagar University, India. Currently, Dr. Das serves as the technical lead for remote sensing and agricultural in the GIS division at the Madhya Pradesh State Electronics Development Corporation. In this role, he applied the satellite remote sensing technology to conduct the agricultural and crop damage impact studies across Madhya Pradesh. His career spans over the 12 years of expertise in geoinformatics, focusing on the environmental applications. Previously, Dr. Das contributed to the World Resources Institute India and serves as a faculty member in the Department of Remote Sensing and GIS at Vidyasagar University for the 2 years. He has prolific research portfolio, having authored 45 peer-reviewed research articles and the book chapters into the reputed SCI-indexed journals. His work demonstrated a strong commitment to advancing the applications of geoinformatics in addressing the environmental and agricultural challenges. With this I welcome you, sir, Dr. Pulkesh Das, sir, to this 1 week FDP and for the today's session. Over to you, sir.
Thank you, Dr. Digambar, for this introduction, and I congratulate you for conducting this event. Uh,
Thank you, sir.
so, with this brief introduction, I'll start my today's presentation. As Dr. Digambar said, I'm working as serving as a tech lead agriculture remote sensing in Madhya Pradesh State Electronics Development Corporation. So, as today's topic suggests on GeoAI for forest cover mapping and sustainability goals, so I'll go through some slide deck I have prepared, and mostly I'll try to focus on forest and agroforestry mapping and monitoring through AI technology. So I'll start with some global overview about the forest resources. So according to FAO 2020 report, so more than one third of the global land cover is covered by forest. And if we go by percentage, Russia is the leading country in terms of total forest cover, followed by Brazil and Canada, US and China. And India only contributes 2% of global forest cover resources. So it's very important to monitor the forest cover resources in India and how we can improve the forest cover area in India. And also India have the international commitment of increasing tree cover, increasing carbon stock, improving the like converting the degraded lands to forested lands. So there are a lot of commitments. So it's very necessary to understand the Indian forest cover and how we can improve the existing forest cover, not only by its area but also through the its more productivity or its more growth. So according to FAO, if we see the Indian forest cover change between 2010 and 2020, so around 266,000 hectare of forest cover has gained in India annually in the last 10 years. So it's a good achievement if we compare with other countries around the globe. So before I start with the AI/ML application part, I'll just go through few basics things like why do we need this periodic forest cover change mapping? Like what are the major application areas? So the very first thing we are interested in assessing the human disturbances, how the forest cover is changing. It could be forest loss, it could be forest gain, and how these are linked with the agriculture activities. Mostly the shifting cultivation in hilly terrains in India. Like if you check the land cover data of Northeast India, you'll find there are like few forest and agriculture land which change like which used to change in alternative years, and it's very difficult to map or identify which are agriculture land, which are forest lands compared to last 5, 6 or 10 years interval. And also you will find like for a lot of our development and forest this removing forest have been to increase the same amount of forest cover in some other areas. So that's why it's very important to see these changes where it's degrading, where it's increasing, and how much it is increasing. And also these are linked with various other natural disasters like when there is a drought, flood, or forest fire, landslide, or cyclone. So what are the impact of such natural disaster on the forest cover or their resources or their health? And also the forest cover has a very good like a lot of contribution on the hydrological condition in a region. So it modifies the river discharge, the groundwater recharge, or it also affects the planting condition, and it has some regulating factor on the soil erosion or the soil nutrition loss. And this forest cover monitoring is particularly important for the forest department who used to develop the forest inventory plans or forest management plan. And if we see the economic benefit people used to extract from the forest areas are the non-timber forest product or minor forest product. In short, we call NTFP or MFPs and bamboo harvesting. So the forest dwellers or in tribal region, people relies on forest resources a lot. So that's why we need a periodic forest cover mapping and monitoring, not only to improve the forest cover in our land surface, but also it's linked with the socio-economic condition of the forest dwellers and particularly the tribal people. Okay. And in urban areas, it is important. Like if you see the recent reports from various big cities, there is a like growing threats of what you call poor air quality. Okay. So it's become very important for us to manage or monitor the forest cover resources and how we can tackle this kind of air pollution by increasing the green cover resources. And also in recent years, like in 2014, Government of India introduced the National Agroforestry Policy. So there it again became like important to monitor the tree cover within the agriculture areas. So these are the basic main purpose of monitoring forest cover. But if we see the National Forest Cover mapping by Forest Survey of India, who has been mandated mapping forest cover resources in India, you will find their methodology is quite simplistic. Like they use visual image interpretation technique, and they apply some very basic digital or hybrid classification techniques, and they produce the forest cover map biannually. And if you see their classification scheme, they mostly so they basically classifies the forest into different density classes, and they monitor these changes at 2 years interval. And in addition to that, they also monitor the tree outside forest or plantation areas. So they apply a 1 hectare threshold for forest cover mapping, and for block plantation or tree outside plantation, they apply some 0.1 hectare minimum patch area. Okay. And this is one of the forest cover map produced by Forest Survey of India in 2021. And if we see the total forest, like including the tree and forest cover, it's roughly 1/4 of the country's total geographical area. And as I mentioned, so FSI maps the forest cover into different density classes. If we check other land cover maps or forest cover resource mapping, like periodic mapping, so we will find NRSC is one of the biggest contributor in this sector. So they produces national level forest cover resources as well as the other land cover classes like agriculture, water body, built up area, or snows, grasslands. Sorry, grassland is again part of forest resources, but barren land kind of classes they include. So, but in NRSC data, you will not find maybe annual or biannual data. So if you check the Bhuvan portal, you will find they have data for some 5 years, 7 years interval. Like if you see the last line, these are the data available on Bhuvan portal. So you can check the land cover changes or forest cover changes between these years. And in comparison to FSI, forest cover mapped by NRSC has more minute classes. Like they take the major species, they classify the orchards, which you will not find in FSI classification. So with these backgrounds, if we see the latest development in global studies, what we will find is there are few global products which have been produced using advanced AI technologies, mostly like deep learning models. And this is one of the highest resolution data available globally, produced by Esri. They have a 10-meter resolution product. And if you know, the Sentinel-2 data is available since end of 2015 or early 2016. So Esri produces the land cover from 2017 onwards. So they produces the annual land cover and for land use and forest cover product. So if you want, you can download their data. Like if you check the FSI data or NRC data, few data are available, but sometimes they are like available in the public domain. Sometimes you have to pay for that. But the SRE Uncover data is a open source product. Like you can download for your study area. It could be a small town, it could be a state, or it could be the entire country. So these data are publicly available. And the good part of this data is they have a very good accuracy at a global level with more than 85% overall accuracy. And they have mentioned they have a lower accuracy for grasslands and scrubland. So Esri has a portal. If you want, you can go and check their portal. And I just took a screenshot, like created a small video. So this is one part of the Mumbai city. If you see, there are some changes in the land cover around this part. So this is the change reduction between 2023 and 2017. So as I mentioned, like you can identify the changes in land cover, or if you want to map the forest cover, you can check their data. So this ACD, as I mentioned, they produces this kind of data at annual scale. But if you have to get such data for much finer temporal resolution, there is one more data is called dynamic world. Again, you can use the Sentinel-2 data so that you can get a 10-meter resolution product. And this is again produced with AI platforms and Google Earth Engine. So here I have a small video created using Google Earth Engine, and what I'll show here is the land cover change between 2 months. So this is 2023 February and 2023 March data I'll be showing here. So if I run this, so this is part of Maharashtra. You'll find like this is the data for February 2023. So now if I change just the month, it will produce one more land cover for the month of March. Yeah, this is now producing the land cover data for the same study area for March. So these are the like global data sets you can use, or like you have the annual scale product, you have monthly scale product, and these are like easily accessible. You don't have to pay for accessing these data, and these are produced using the AI ML techniques. Now I'll show some of my co-authored articles here. So this is one basic study we did in 2019, where we compared two models like the logistic regression and random forest algorithm, and we compared their accuracy, and both of them provided more than 95% overall classification accuracy. And in this exercise, we used the Sentinel-2 data, and as a reference, we used labeled pixels. This is one more example from Northeast India. Our aim was to map the shifting cultivation areas using AI/ML techniques. So I'll just quickly explain this figures on the right hand side. So if we have the satellite images, how we can identify the shifting cultivation areas, and then we can create our label samples, so that we can automate the entire process and produce such shifting cultivation map for entire Northeast India or a small region. So if you check the images on the upper right hand side, the points A, B, and C on the left hand side figure in 2014. This is a false color composite image where I used the shortwave infrared band as in the red channel, near infrared band passed through green channel, and red band passed through blue channel. Now, if we see the land cover changes between 2014 and 2015, we'll find that in points A, B, and C, where those are like green pixels, these are basically forest cover areas. So in 2014, this region A, B, and C, those are like forest cover areas in 2014, but in 2015, you'll find some changes happened. So if you have this particular band combination, and if you get this kind of bright purple feature in your image, so these are the deforested and burned areas. So these points like region A, B, and C, these are forest in 2014, and those were deforested and burned in 2015. So if we check the same thing for region D and D, we will find that these are like already deforested or burned area in 2014. And in comparison, points F and G, these were forest in 2014, and they are still remain like undisturbed in 2015. So those are the no change areas. So if we interpret the satellite images using some ground knowledge or some image interpretation knowledge, we'll be able to identify the land cover changes, and depending on the data availability, we'll be able to map the shifting cultivation areas, creating labeled points in these areas. So in this study, we took the Sentinel-2 images, and we all know that this shifting cultivation or zone cultivation, it's basically a conversion of forest into agricultural land, where the farmers, they like clear the forest cover land, and whatever dead plant material remains in that land, they used to burn those plants material that enriches the soil nutrients. So they used to use this land for like 2 to 3 years or 4 years for agriculture, and then after then they abandoned the land, and eventually when they abandoned this land, natural forest used to like regrow, and then it these patches again become like forest cover in 10, 15, or 20 years period. Okay, so this is this like removal of a tree cover, then agriculture, and then growing of forest. And also again, like what they does basically, when the tree grows in these lands, they again used to return to that land, and then they used to do the same procedure like removing tree cover, burning those dead plant materials. This entire thing is called a zoom cycle. So in recent years, various articles have reported differently. Like few articles have mentioned that this entire cycle, which used to be 10 years, 15 years, 20 years in some region, those are now reduced to 5 to 10 years only. So that's how it's a very big challenge to identify these areas where the tree cover or the agriculture is changing very frequently. And also this kind of land conversion removes the carbon stock stored in the tree cover. Basically, those are removed from the terrestrial ecosystem, and because of that, there used to be like greenhouse gas emission, not only from the burning of the dead plant material, but as the trees are removed from the ecosystem, it automatically reduces the carbon sequestration potential. And as we have like lower tree cover in the region, so it creates the soil to be more like vulnerable to erosion, or it also increases the surface runoff. So that's why it's very important to map these shifting cultivation areas so that the suitable management plans can be developed, or alternative practices can be developed, or policies can be developed. So here in this case, we took Sentinel-2 satellite images and also Landsat satellite images, and we tried to see the changes in such areas where shifting cultivation is happening. What are the image values showing? So we applied spectral indices. So spectral indices basically highlights few land cover features in the image. So normalized burn ratio, it's one of the very important indices to understand the burning of this kind of dead plant materials. So if you see there's a like distinct difference in the normalized burn area index map. These red patches are showing the recent burn areas. Same thing you can also see in the NDVI change maps when you have NDVI maps for two different time periods before deforestation and after deforestation. And if we create a change map, it is easily visible where land cover is changing. And again, we applied the normalized difference moisture index. If you check the moisture also, you will find a sharp change in the moisture condition. And if you see the elevation data or the slope data, you'll find most of the shifting cultivation happens in the high altitude or moderate altitude. So if you take elevation as one of your parameter, you will find there is a improvement in your modeling accuracy. Okay. So we applied the random forest machine learning algorithm, and we could produce our like shifting cultivation map with more than 90% classification accuracy. These are the shifting cultivation map for three different states in Northeast India. It's from Meghalaya, Nagaland, and Manipur. And one more good achievement was like we developed this model for 2017 and 2018. So whatever changes happened between 2017 to 2018, we mapped those areas. And the model we trained for this period, we applied to 2016 and 2017. And we could produce the accuracy with about 90% classification accuracy. So we assume that this is a very robust model we could produce. So if we have such kind of models, we can apply to some other years or some other region or other states in Northeast India so that we can map the shifting cultivation areas at periodic intervals. Now I'll briefly talk about the agroforestry. So this was not my direct project, but it was a collaborative project with one of my friends. So in this study, we tried to map the agroforestry suitability areas in Odisha. So we started with a small landscape. So if we go by definition, so agroforestry is basically a form of like growing tree cover in various forms. It could be intercropping or a boundary plantation or a home garden. So like intercropping is the upper left hand side image. If you see, we have some trees, some fruit trees is planted in between agricultural land. So this is basically called intercropping. So in the early stage, the farmers they used to produce both crop and they used to get the benefit of the like fruit trees or some commercial trees. And on the bottom image, we could see these are the boundary plantation. So along the boundary of a crop field, we can plant some trees, and we can get benefit of both the agriculture and the tree cover. So although these are like uh, these kind of initiation have been taken in last 1 or 2 decades, but this is a old practice in India. It's not a new practice in India. Like let's say home garden, we used to grow our like few common fruit trees in our backyard. So and also some vegetables in our fallow like open land in around our house. So these are like very traditional practices we have. But with the government support, farmers used to apply or like grow these trees in farmlands with government subsidies and government support. So if we talk about their benefits, like agroforestry provides like the fodder, food, and livelihoods. It maintains the biodiversity, and it also improves the air quality, controls the microclimatic condition, reduces the soil erosion. So agroforestry has a lot of benefit to not only our economy but also to the environment. And as I mentioned, India's national agroforestry policy was launched in 2014 in February. So the task was to map the agroforestry suitability areas in Bolangir district, Odisha. So we had some ground data points on agroforestry and non-agroforestry areas, and we took a lot of proxy data like soil, the topography, some proximity variables, climate, and then this RF is the rainfall. This is the distance to build up. So we took data from different your themes like soil topography, proxy, climate, and then we developed a machine learning model using our ground reference data. And so with the help of random forest machine learning model, we could produce the suitability map for this entire landscape. And then depending on the existing land cover type, like what is the agriculture practices or kind of land cover we have, we could prescribe what are the suitable interventions the farmers can implement in their property. So when we have double crop lands, like those are like very fertile lands, we do not want to deviate the farmers. In those areas, we suggested farmers to uh, implement the bound plantation or boundary plantation. But those where farmers could produce only one crop in a year, they remain fallow in the dry season. So in those areas, farmers can apply both one plantation and intercropping. Okay. And again, when there is the settlement areas, those areas could be suitable for home garden. So around the houses, if there is any vacant land, unutilized vacant land, so people can grow home garden in those areas. But where there is like wasteland kind of area, those are like unproductive lands, so those could be favorable for block plantation or bulk plantations. So if we have a suitability map and if we have a land cover map, we will be able to produce such kind of suitability map for different agroforestry interventions. So once we created a case study in Bolangir, we implemented this entire like exercise to entire state of Odisha, and we could produce a suitability map for the state of Odisha in terms of agroforestry interventions. Now, here we have one more example from agroforestry. Here we tried to map the carbon stock or the above biomass. So if we take by the value, so half of the above ground biomass is nearly similar to the carbon stock. Okay. So as I mentioned, like India has a lot of international commitment on improving the tree cover, but they also have the commitment of improving the carbon stock. So India is committed uh, to improve another 2.5 to 3 billion tons of CO2 through forest and tree cover. So this kind of interventions not only, as I mentioned, not only useful for socioeconomy, but it also useful for our environmental studies, or if we have to improve or mitigate the climate change or reduce the global warming. So in this case, we blended the Sentinel-2 optical data and Sentinel-1 microwave data. And similar to the previous study, we took different spectral indices, different spectral bands, and then from the Sentinel-1 microwave data, we took different proxy variables in different polarization bands. So in Sentinel-1 data, we have the VV and VH polarization bands, but we create some proxy variables using these two indicators. And from the field, we could collect some field level biomass data. So in field, we go in an agroforestry area, plantation area, we count the number of tree cover, we check their tree height, their guard size, and there are allometric equations. So these equations are available for mixed species, or there are like species specific equations. One can apply those allometric equation and estimate the biomass or the carbon stock in the field. So once we have this kind of field data, we can develop various machine learning models, or regression models applying machine learning algorithms. So we compared three machine learning models, namely RF, SBM, and ANN, and then we compared their accuracies. So on the left hand side, we have the variable importance from different models, and on the upper right hand side, we could see the above ground biomass map predicted by the three different models. And if you check their magnitude, there could be some variation in their magnitude, but their overall pattern is similar. So uh, in this study, so we tried to map the above ground biomass. So if we take half of the above ground biomass, we will be able to estimate the uh, carbon stock, and if we multiply that with the value of 2.67, we'll be able to measure how much CO2 has been sequestered. Okay. So these are the like few approaches we can apply for our carbon stock assessment. Now I'll present one study from Pune Municipal Corporation. So in this project, this is one of my project at WRI. So I served 3 years at WRI India. So at WRI India, I managed one project. Basically, I managed this project. So here we tried to map the tree cover change in Pune Municipal Corporation between 2016 and 2020, and also we tried to map the tree canopy height. So our initial initial plan was to visit Pune, collect some ground data on the like tree cover, the kind of species, their canopy height, but we could not go to field due to COVID and all those lockdowns and travel restriction. So instead, we used the Google Earth imagery to generate our data points, and also we used the visual image interpretation technique, and we generated our data for our classification and regression studies. Okay. So this is like very simple flowchart. We took the Sentinel-2 data, and through visual image interpretation, we could produce the training data for land cover classification. So we produced the land cover map for 2 different years and then identified their change. In addition to that, we also took the JEDI LiDAR data. So this JEDI LiDAR data, it's not, maybe I have some, no, I don't have that slide. So anyway, this LiDAR data provides a product on the canopy height. Okay. But this LiDAR data products are not available for each pixel of an area. So they are not continuous data spatially. If you check the JEDI data, you'll get like few plots, circular plots they have, and they could produce the pixel level canopy height at 25 meter with 25-meter radius. So they produce some continuous data using that data, but the original data, if you see, those are like plot level data, and each points are separated by some 800 meters. So it's not a continuous data spatially. So we took that data and again developed regression model using machine learning models and applying that model to the Sentinel-1 and Sentinel data, we could produce the tree canopy cover map for entire Pune city. So this is the outcome from the land cover mapping exercise. So we have a land cover map for 2016-17 and 2019 to 2020. So at the study area scale, you may not be able to identify the changes in land cover, but if we have a close look, we'll be able to see the changes in tree cover. So for reference, I have taken the Google Earth imagery here. And if you see on the lower middle image tiles, you'll find this is an area barren land, like classified as barren land in 2017. You'll find some like urban growth has been happening, like some your settlement areas have increased in this area. Basically, some buildings has emerged between 2017 to 2020. So these changes we could identify using our classified maps. Again, I have some example on the upper right hand side. Although we could not go to field, but from our Google Earth imagery, we could easily see the changes in land cover, which are like previously dominated by some tree cover, some grassland, croplands. Now some settlement area has increased. So basically, this is the one of the Pune metro station that has been constructed between 2017 to 2020. And here I have one more example where the tree cover has been replaced. Like basically, here the tree cover has been removed. So in 2020, those are classified as grasslands. Maybe some small like remaining or under canopy grass or scrubs could be there, but the important part is there are some tree cover changes. So with this kind of approach, we'll be able to automate this kind of land cover mapping exercise, and we'll be able to identify where tree cover is increasing, where tree cover is decreasing, or any other land cover changes we'll be able to identify at 10-meter spatial resolution. So with 10-meter spatial resolution, you can like map at least 20-meter by 20-meter areas. Yeah, so this is the canopy height prediction using the LiDAR data. I have this graphical representation here on the lower left-hand side. So as I mentioned, the LiDAR data, they have a circular plots. So they used to measure the uh, background background reflectance in terms of the elevation. So if you see this waveform, you will find there is a like there are like uh, two major peaks are there. So the major peak around the ground elevation is called the ground reference or ground return area, and all other peaks corresponds to the different canopies along the canopy height. So if we have this kind of waveform, we will be able to identify not only the tree cover height, but also their like canopy, what is the length of that canopy. So as I mentioned, the JEDI data is not available at continuous pixel. They are available at basically plot level. So this is the JEDI data we use in our training uh, develop like model development as a training data. And on the right hand side, we took some 10% or 20% data for our validation. So using the LiDAR data, we could produce the canopy height for all the tree cover areas in Pune Municipal Corporation. And if you see our model, uh, nicely predicted the canopy height in this case. And on the upper left hand side, we have the predicted map. But if you see this bar diagram with a cumulative frequency line, you will find like most of the trees in Pune Municipal Corporation having a canopy height of less than 20 meter. So most of the trees we can say like those are mature trees or younger trees, but old trees above 20 meter of height is very less in Pune Municipal Corporation. So as I mentioned, this was one of our study at WRI India. So with continuation of this same JEDI LiDAR data, we could produce the canopy height for our all the tree cover in India. So this was one more collaborative project with my PhD supervisor. So here again we applied the random forest machine learning model and we took the JEDI data as our reference point. In case of our optical data, we took Sentinel-2 data, but we took the pulsar microwave data in as one of the independent variables to train our model. So these are on the left hand side in the flow chart. These are the input reference data for our model development. We created some proxy variables and then we trained the model using the JEDI LiDAR data. Okay. And we could produce the canopy height map. So here in this case, we created models for different forest type. Like for evergreen forest, we created one model. For deciduous forest, we created another model. So in this example, we developed different models for different forest types. And with that, we could produce the canopy height map for entire India, like for all the tree cover area in India. And you can see the final outcome on the left hand side. And then we have some uh, chart. Basically, these are the histogram chart. So it shows the canopy height and then number of like observation, or you can say like the proportion of tree cover in different canopy heights. So I have few more slides. So initially, my plan was to stop here, but I guess we have some time. Dr. Digambar, Dr. Prakash, what do you say? Shall I proceed or
Yes, sir,
shall I
we
stop
have
here?
time. You can.
Yeah, we have a lot of time remaining.
Yeah.
So this is outcome of my postdoctoral research in USA. So this has been published very recently. So this study may not be a good fit for India, but maybe in future this kind of product or study could be more relevant for India. So I'll explain why this is more relevant in USA. So in USA, let us start with India again. So in India, most of the tree cover, if it has a minimum area of 1 hectare, those patches we call as tree cover, and then it's uh, it's restricted that you remove trees in those areas. If it has a tree cover area of more than 1 hectare, then that area will be regulated by the Forest Survey of India or the Forest Departments of India. Even if it is a private land, still it is difficult to manage those areas without Forest Department's permission. But in USA, more than 70 to 80% or more than at least 50% of the forest land are privately owned land. And they used to manage their land and they are like very methodical. Like in India, people, even if they have trees in their land, sometimes they do not really care about their recovery in their property. Sometimes those are getting affected by some disease or pest attack, or sometimes they are experiencing some degradation. People often ignore them, but in USA, people are very careful about their tree cover in their properties. So in every summer season, like in this study, I have a collaborator from the Maine Forest Service. So Maine state is there at the upper right hand side. It's like northeast part of USA, bordering to Canada, and the nearest landmark is Boston. It is like some 2.5 hours drive from Boston. So at least in this area, what I could see is people are very careful about their trees, and in every summer, if they find anything wrong goes with their trees, they used to dial the forest department or the forest land managers, and they seek their help. Like in my trees, I could see some pest attack or some unusual thing is happening. Can you please come and check? And can you please suggest what we should do to prevent this damage? So they are very particular. So in that sense, this study is quite important in this part of USA. So the novelty in this research was to map the live ground ratio. So I guess a lot of people know about this leaf area index. So leaf area index is the amount of leaf layer corresponds to the same area in the land. So if you like remove all the leaves from a tree, and if you create like layers of leaf cover for a particular like unit area. So let's say if you create a leaf layer of 1 meter square corresponds to a ground area of 1 meter square, then we call them the leaf area index is 1. But for a 1 meter area, if all the leaves of a plant produces 3 layers, like if we have to, like in this case, we have to remove all the leaves. It is kind of a destructive approach. So you have to remove all the leaves, and then if you could create 3 leaf layers per unit surface area, you will say the leaf area index or LAI value is 3. But there are some instruments are there like plant canopy analyzer. So those kind of instrument, or if you have a fisheye lens with a camera, you can collect the photos beneath the trees, and then analyzing those photos, you'll be able to estimate the leaf area index. So in that case, you don't have to harvest all the like leaves from a tree. So these are the like proxy methods one can apply for leaf area index assessment. So leaf area index studies is very popular throughout the globe. You will find a lot of research article on this, but there are very limited studies on the live ground ratio or LCR. So live ground ratio basically represents, it's a very simple term, very simplistic thing, but it's an important thing and quite understudied, at least in terms of geospatial data analysis. So what it shows basically, if you have a tree, if you have the height of the tree is B, and you have canopy only for the height of A, so the live ground ratio will be A by B into 100. So in terms of percentage, you will get the live ground ratio. But you will not get the live ground ratio product for, let's say, state of any state or global product are unavailable on live ground ratio. But if you see the Modis data has a LAI product for the entire globe. They have monthly product, annual product, different products are available. So in that sense, it was quite interesting to create a product on live ground ratio using satellite data. So in this study, we took the Sentinel-1 microwave data and Sentinel-2 optical data. And for our live ground ratio estimation and LAI estimation, we applied random forest algorithm, and then integrating this LAI and live ground ratio with the canopy height and stand density. Mm. So Sorry, I could hear some noise. Do you want to say something? Am I audible, Digambar?
Yes, you are audible. Yeah.
Yes, sir, you're audible.
Okay, thank you. Thank you for confirming. So we integrate the leaf area index and live ground ratio product with canopy height and stand density, and we could produce a eastern white pine stand health index. So again, this was one more novelty. There are like no such data available that directly provides an estimation of stand health, at least for this eastern white pine species. And another, sorry, I'll just take a quick break. I'll have some water. So another important component was the stand density and the canopy height. So one may ask, why did I develop this product for this particular species? Why not for the entire tree cover or all the tree cover area in this entire state? Why only this coastal region? So in this state, if we see the coastal regions are dominated by this particular species called eastern white pine, and this particular species has a typical uh, like behavior with other eastern white pine trees. So you'll find when these trees are sapling stage or are in younger stage, they can accommodate a lot of trees in a small area. But once the trees grows to their maturity level or their old ages, you'll find they used to repel the other eastern white pine trees. So at younger stage, you will find the stand density, the number of trees in an area will be very high, but as they grows, they becomes mature or old, the tree density gradually decreases. So the major factor is they used to have the competition for resources. Okay. So that's how, if you have more trees in an area, the trees growth will be very tardy. They will be very lean, and their economic value is to be very low. But if you have very good well grown tree with very big your trunk, those are very you see, economically very viable or very important. So that's why it's very important to manage the tree density with their age. So as I mentioned, as the tree grows to their maturity level, we have to maintain a lower stand density. So that age factor we took from the canopy height. Okay. And density factor, stand density factor, we took the stand density index, and those are basically this leaf area index and live ground ratio that denotes how healthy those trees are. So we generated a number of proxy layers using our Sentinel-1 microwave data and Sentinel-2 optical data. So we took the VPPH band and their ratio, but in terms of Sentinel-2 spectral indices, we took some how many 7 or 8 spectral indices. Then we had the elevation data, the canopy height data, and stand density index data. So on the upper left-hand side, you can see the overall flow chart of data flow. So we had this kind of indicators. We took satellite data, applied regression techniques through machine learning algorithms. We predicted the live ground ratio and leaf area index, and then using the canopy height data and stand density data, those are like publicly available. At least in USA, those two data are publicly available. So integrating these 4 data, we created a stand health index on the upper right hand side. This could be very small text to read, but if you want, I can share the article with you. So with the increase in height, so as I mentioned, we took four different layers: canopy height, tree density, live ground ratio, and leaf area index. So with increasing height, we applied a lower threshold of tree density, and then we applied the live ground ratio. It should be at least 40% or at least 35% for mature trees, and for old trees it should be at least 30%. And then depending on the leaf area index value, we classified the trees into different health categories. So on the lower left hand side, these are the two layers we could produce at 10-meter spatial resolution, and this is their like variable importance chart, their validation accuracy. And applying that decision tree which I just showed, we could produce a health index map for all the eastern white pine trees in the state of Maine, like uh, at least those in the coastal region. So these red patches, those are the unhealthy stands. Then the green patches shows the healthy stand, and then the orange patches shows the moderately healthy stands. So, uh, so these areas where we have the unhealthy or moderately healthy stands, these are particularly important for the privately owned forest owners, or there are like in USA, there are like multiple what they call like startups. They used to manage the forest land for others. So they used to uh, charge some money to the beneficiaries, and in favor of them, they used to manage the land. And then once they harvest those trees in their property, they used to share the money earned from that forest, like selling those trees. So it's important for both of them and also for the forest departments to see where we have healthy and unhealthy stands. So we could produce this map at 10-meter spatial resolution. So this is one of like the highest spatial resolution data what we have in the open source. So we recently published this study in ecological informatics. Yeah, with this I'll stop here for now. Dr. Digamba, Dr. Prakash.
Yes, sir.
Yes, yes,
I
we
guess
can
I
hear you.
finished
Thank you,
much
Dr.
before.
Pulkesh Das, for sharing your valuable insights with us. Now it's time for us to engage in question and answer session. This is your chance to ask the questions to the speaker. I welcome all the participants to participate into the question and answer session. If you have any doubts, you can directly ask.
Hello, Das sir.
Answer, yes.
Yeah.
Yeah.
Can you hear me?
Yeah, you're audible.
Yes, sir. Yes, sir. You're audible.
Yes. It is very nice presentation, sir, and it is very informative.
Thank you.
Sir, I have just one question. Generally, this kind of research is restricted to generally government or any specific research institutions, right?
Mhm.
Those who support the government. And, but as an academia, how and where to contribute in such kind of research?
Like, can you just like are you talking about the like overall studies, or do you have any particular study in mind, like
No,
agroforestry
this
or forest,
remote
or in
sensing
general?
area. Yes, in forest cover mapping and everything.
So as I started with my presentation, as I mentioned, like the Forest Survey of India or NRSC, if you see there, methodologies. Most of them are like visual image interpretation or very basic digital classification of the data. So if you have very good understanding about the machine learning or deep learning models, it will be a great contribution to the academia. If you could produce some models that automatically maps the tree cover changes at a very high resolution, at least at 10-meter resolution, if you could produce a data and that is applicable not only to a particular landscape or a state or a district, if you could produce a model that produces such kind of land cover map or forest cover map for entire India, that will be a very great contribution. And I hope like that will not only serve your academic purpose, but that will also serve the national purpose. Okay. So there is a big gap in India on producing such kind of data using AI/ML techniques. Like you will find a lot of researchers, including me, we produces this kind of data for small landscape or for 1 or 2 years when we have a project for 2 to 3 years, 4 years. We produces a map and then we publish that and then we forgot. But if you can create a platform or some web application or some models that can map this kind of features on the land surface periodically for bigger, like large scale, that would be a good contribution. And also, you'll find there are some global products available on above ground biomass for entire globe at different like spatial scales. And most of them you will find it's available at very coarse resolution, maybe few kilometer. So there is a lot of gap on that aspects also. If somebody can produce data on above ground biomass stock at very finer resolution like 10 meter, 20 meter or 30-meter resolution, that will be again great contribution to the society. And if you talk to like professionals from various government departments, you will find they often say like NRSC data or FSI data have some like disagreement with the actual land cover. So it is also very important. You have to produce such data with good location accuracy. It should not produce like in the slide deck I didn't mention, but if you read my Pune article, you'll find the Pune Municipal Corporation spent a lot of money on uh, collecting data on the tree cover resources available in Pune Municipal Corporation. And you will find their data is like very like unrealistic data. There are like what I could see or what I reported in my article, like I could see in a region where hardly there could be some 30, 40 or 100 trees, but the surveyors who collected the data, they showed that there are like more than few hundreds or few thousands of points. So there are a lot of scope. You can produce those kind of high resolution data for your academic purposes, but if you talk to the departments or professionals, there would be a, like good buyers of your data or good application areas. They always welcome you if you use or if you work with them and produce such kind of good products for them.
Thank you, sir. It is very useful.
Sir, one more question. Is there any data set where you have worked, the IITs has published it for the open for the other peoples?
From
Yeah,
my study,
you have worked on the different data sets. So any IIT has make it open for the other to research?
Yeah, like let's say most of the data which I have used are like publicly available data. So if you uh, use that data, and if you apply the models I have applied, or if you apply your own different models, you'll be able to replicate the kind of data I have produced. And if there are some data which you do not have access to, you can reach out to me, or if you need any particular data, if you need any suggestions, or you can get the data, I'll be always available to help you from where you can get the data. If it is available in the public domain, I can help you finding that data. If you need some data from my studies, I'll be happy to share if you
Thank you,
need
sir.
that.
Is there any other question from participant side?
Hello,
Yes, sir. Yes,
can you
go
hear me?
ahead.
Yes, Prakash.
Yeah, yeah, yes, yes. Thank you, Dr. Pulkesh, for this presentation. Uh, in the slides, you mentioned about mapping home garden, regions, but these
Mm.
gardens will be very small in their aerial extent. What kind of satellite images can offer that resolution that will be able to map these areas?
Yeah, actually, you highlighted a very important aspect. Like it's very critical to identify the home gardens. So, depending on the data availability, there could be differences in accuracies. So, let's say if we use the uh, publicly available data, let's say Landsat or Sentinel. So, our usual approach used to be, if there is a settlement area and if we see there are some tree cover, we used to classify them as a home garden. But if you really have to map the tree cover in the backyard, uh, the other moderately cost data, I would say, is the planet scope data, which is 3-meter resolution. And the good part about the planet scope data is sometimes they used to offer the data at free of cost. So if you are an academician, if you write to them, and if you request them to share the data for a small area or a like city area, sometimes they used to offer the planet scope data at free of cost. And recently I could see there are some global initiatives. One initiative is NICFI. So through the NICFI program, one can access the planet scope data freely, but the NICFI program has some collaboration with different government institutes in different countries. So you can take a look who have access to the NICFI data portal, like NICFI data. You can also request PlanetScope to either access the data directly or through NICFI program. And for students, I guess they'll be happy to share the data for a smaller landscape. But if you want to map that recover at species level, so in that case, you have to use at least below 1 meter resolution data. And if you have a very high resolution drone data, that will be like one of the best data available for agroforestry mapping. So recently, from my PhD lab, uh, there is one boy who has recently published an article. Maybe I can show you quickly. So they basically use very high resolution data. I'll just reshare my screen. I guess you could see my screen. So
Yes, sir.
this is a recent publication from my PhD lab. So they mapped the individual trees like agroforestry of mango plantation, then at different density. They also mapped the coconut trees at different density classes. So they applied this deep neural network, I guess, multitask DI unit they applied. So if you are very good in deep learning techniques and if you have access to such high resolution data, you can map at species level.
Yeah, yeah, yeah. Thank you so much.
So depending on your data availability and your resources, you can map from 10 meter to like few meter to few centimeter scale.
Thank you very much, sir, for sharing your work and solving the doubts of the participants. So now it's time to express our sincere thanks to our eminent expert, Dr. Pulkesh Das, sir, for his insightful presentation on Geo-AI in forest cover mapping and sustainability goals. Sir has covered the global forest resources statistics, what is the need of these studies, and covered his various published studies in the different areas. Sir has also enlightened us on the agroforestry in different areas, forest area monitoring, and the case studies on the predicting the forest canopy height from LIDAR and multi-sensor data using machine learning over the India. Sir, we are truly grateful for your time and expertise that you have shared with us. Your session has given us a lot of things about various aspects and the applications of Geo-AI in forest cover mapping and sustainability goals in India and outside the India. So with this, I will say thank you again for joining this session and giving your time to this 1 week ATAL FDP and giving the more areas of research to the participants. All are the faculty members, so they can give the statements to their researchers, students, BTech, MTech, and PhDs. So thank you very much, sir. On behalf of RAIT and UI Patil team to be University, I appreciate a token of love to you, and uh, I hope we'll see once again in the next upcoming future FDPs.
Uh, thank you, Dr. Digambar, and thank you, Dr. Prakash, for inviting me in this nice lecture series. And thank you all the participants for patient
Thank you very much,
listening
sir.
and your queries.
Have a great day,
Have a
you
great
too, sir.
day.
So I request
Yeah,
participants
thank you so
to
much.
tomorrow's session will start at 2. So the timings are different for tomorrow. So in first 5 days, we have taken from 6 to 9. And so tomorrow is our last day of the FDP. So we'll start at 2 and ends at 5. Maybe after the sessions, we have the uh, validatory session for maybe 20 minutes or 30 minutes. So I request all the participants to join at 1:45 or 1:50 p.m. So link will be remains the same. Thank you very much for joining us in today's sessions.
Thank you. Thank you. Bye, everyone.